This is the focus. And I actually got notes here. Little notes, little post-it notes. The first post note says, how about that? Okay. First thing. Rate of change of A with respect to B is delta A over delta B. I'm going to have to zoom back just a little bit. Come on, zoom. Zoom a little more. Go up. Zoom a little more. Go back down. Yeah, that probably works. And it almost went out of focus, but it stayed there. Okay. The rate of change definition. Limits applied derivatives. If I'm writing too small, you move up a little closer. Forget out your telescope or whatever. I got a lot to put on the board here, okay? So limits applied derivatives. So average velocity is delta V over delta T. That is the rate of change of V with respect to T. And it's not delta V, it's delta S. V is then dx dt for continuous position functions. And position functions are in the physical world continuous, at least until you get to the quantum level. And similarly for acceleration, you get the derivative of V with respect to T. Acceleration constant implies one that your position function 1/2 at squared plus V naught T plus X naught. I've derived that in detail at least a couple of times. So if you have to review it, okay, but I could well ask you on an exam to derive from first principles the equation for uniform acceleration.
The answer is yes. You should be able to. The long answer is probably.
From this, we get all the equations of motion. The book gives you 4 equations of motion. You need to know those equations. You need to know how they get there from here. Gives you a perspective and a course, and it's simple algebra exercise. We're talking premises and conclusions, okay? Premise, if your acceleration is constant. Premise is the acceleration is constant. Conclusion is X equals this. And of course, the same thing would apply to Y or Z if you're in 2 or 3 dimensions. You have an X, a Y, and a Z. So I'm not going to write all that out. Oh, there it is. Okay. Thank you, Hal. Second one. I'm getting way ahead of myself in my notes here. I want to make sure I'm not forgetting something I'm going to need in 5 minutes. So, yeah. Don't leave you anymore. Okay. So that force is mass times acceleration. And I'm going to interject something that's not in my book. We've got to use it because it's relevant to what we had for homework today in the last assignment of the course. Once you have this, net force equals negative kx. Implies acceleration is k over mx. So x double prime is negative k over m times x. Implies x equals a times the cosine of omega t plus phi, where phi is a phase angle. I'm not going to go into all the details of how these are used, but you use this during your homework. Another form of your function x is b cosine of omega t plus a sine of omega t. And one of your homework problems dealt with how a and phi are related to b and a c. I think I'm going to change that. I don't want to keep things. And also, omega is the square root of k over m. And much of your homework is learning how to use these equations, model stuff we saw in lab last time, or similar things. And this implies, this is a big deal, so I'm going to go ahead and do it out here. Circular model, circle of radius A, point moving. The velocity omega t plus phi, and you get this y coordinate, this x coordinate, where x is a sine of omega t plus phi, y equals a cosine of omega t plus phi. all of this follows from F net equals negative KX. So the premise for everything here is F net equals negative KX. Premise for most of classical mechanics is one of the big ones. All three of them are really important. Newton's first, second, and third laws. This is Newton's second law. Premise here is acceleration constant. Okay. So I've kind of digressed in the order of things we do in physics. This is like the first thing we did. This is like the last thing we did. But they both result from Newton's second law. Okay. Now, we combine this with this. Okay. The acceleration is constant. The F net is constant. You can conclude that F net delta x is changing 1/2 mv squared. You did that. You just plug A equals F net over m into one of your equations of uniformly accelerated motion. One says Vf squared equals V naught squared plus 2a delta s. Okay? Or 2a times x minus x naught. Plug it in to another equation. You get this. Okay. Don't have time to go through all the details, but just a little bit of calculus, just a little bit of integration. And of course, we can't assume integration in this course because it's not a prerequisite. An introduction to integration generally is part of first semester calculus. But y'all both in multivariable calculus. So, you know, for that to have a little bit of calculus, got to understand a little bit of calculus, not just be able to do the operations. Okay. So we want to think through why this is. If you want to go over this later, if there's time today, fine. Time next time, that's all right. Want to meet for an extra lab session on Friday, we can go over more stuff. Okay, so anyhow, add a little calculus. And you got vector operation. I'll just say n vectors, okay? Know about vectors. That's your work energy. This is a line interval, which you've only recently seen in polynomial calculus, okay? And that's something I'm really going to require you to know. They're probably going to appear in your exam with multivariable, though. So, you know, kill two birds with one stone. And all we're saying here is that this just generalizes to this. Now, the vector form of this, well, that's something you should understand because it was the first thing you saw in work energy, where you're moving at an angle like this, and you got forces in this direction. I gave you your F dot delta S. Okay? You might want to go back and review that. I don't remember which assignment it was in. It's one of the assignments right at the beginning of work energy. Okay? So you get this also. The integral of F net dt is the change in mass times velocity, where F net and velocity are both vector quantities. And that's delta P. Now let's see. And right here, you have your definition of kinetic energy. You have your definition of momentum. That's just how I wrote it down, isn't it? Okay. I don't know what happened to the two that I dropped. Probably stuck to the bottom of my shoe somehow. That's okay. These are just wide lines. Okay. Now, if you have a conservative force, change in potential energy is equal and opposite to the work done by the conservative force. Now you have to understand that the work done by a force is understood to be the work done by the force acting on your system. And like Newton's third law, the system exerts a force, an equal and opposite force on this conservative force, and does work of the opposite side. Okay, so we got to kind of state that. So I'm going to say that's F conservative. And we usually don't write this by, but that means by the force acting on the system. Actually, I'm not going to say by, on. Okay. Conservative force acting on the object or system. So F net being equal to F conservative plus F non-conservative. That means that your work being equal to F net dot delta S or equal to line integral of F net dot ds is equal to I'll write it this way. You can think, if you want, of just an F conservative times dot delta S or an F non-conservative dot delta S. You can even say, okay, this is along the x-axis. So it's just F conservative times delta X and F non-conservative times delta X, right? So, this encompasses all possibilities, including just one-dimensional cases. Okay, so from what we see here, the integral of F conservative ds, or just F conservative dot delta S, or just F conservative times delta X, is going to have to be the negative of the change in potential energy. And of course, this non-conservative force is a force that's acting on the system in addition to whatever conservative force. So for example, something's moving through the air, conservative force of gravity is acting on it, okay? But you have air resistance, and that's a non-conservative force, because it's not path independent. Move through the air in this direction, the force of air resistance is this way. If you move through the air in this direction, the air resistance is in the opposite direction. It's not path independent. Like gravity, you go up, gravity acts down. You go down, gravity acts down. Doesn't change. Now, if you go far away from the Earth, okay, well, the gravity that acts between here and here, it falls off. But if you come back, it increases. It's always in the same direction. And the force at every point is the same, whether you're going out or coming back. That's the conservative force. Well, okay, so we get this. And of course, work by the net force, should have done work net, is negative delta PE plus work. I'll just write an NC for non-conservative, understanding that the non-conservative is the non-conservative force that acts on the system rather than the non-conservative force the system exerts on whatever's creating the non-conservative force. Now, the work by the net force, as we see up here, is equal to the change in kinetic energy, right? You got to make a connection because I don't guess I wrote that out. But I can do that. I can say that the work by the net force is the change in kinetic energy, because this is the work by the net force, and this is the change in kinetic energy, right? And here we say this is impulse. And this is change in momentum. So here we have our net force, or our work by the net force. Here we have impulse. The only difference is the impulse is a vector quantity in the first place, right? And it's what you get when you integrate the force with respect to t, or just multiply the average force by delta t, okay? Up here, it's a dot product, which means it's not a vector, it's a scalar quantity, and it's changing kinetic energy. Okay, points you want to be sure you understand. In any case, work by the net force is this, as we see. Work by the net force is changing kinetic energy, as we see here. So we have this. The work by the change in kinetic energy is not equal and opposite in general to the work to the change in potential energy, which people keep wanting to say. That's only true if the work done by the non-conservative force is zero. So the work done by non-conservative force equals zero implies and this is a special case. No room to write it, but I'll write it anyway. So if you try to apply delta KE equals negative delta PE, you better not do that if there are non-conservative forces involved. It's not a general rule. And if you understand how all these things follow, you understand that it's not a general rule, okay? Okay, well, there's most of our framework of mechanics. Let's work out a few more details. We have conservation of energy, we have impulse momentum, we have equations of motion for uniform acceleration and simple harmonic motion. Okay. Two cases of different kinds of net forces. There are a lot of details we're not filling in, but everything else that we do follows stuff. Okay. Now let's back up here. Something I didn't even put in my notes, but it's real important. As I did this late at night when I was really tired. Okay, so let's look back. Acceleration equals zero. If and only if F net equals zero. Okay. Net force is zero if and only if sum of your forces in all directions is zero. Therefore, statics of non-rotational objects, but I'm going to include rotational objects. So I'm going to talk about torque before I talk about torque, because we've already talked about torque. So I'm a little out of order here. Um, Net torque is zero and only F angular acceleration is zero. Okay. Therefore, static. You know, it's glorious and sometimes gory detail. Now, having said that, and where we position this whole thing in this scheme, it's not going to be positioned in the perfect place. If we position it here, at this point, well, in the first place, this could follow this. Well, this, okay? But since it also encompasses rotation in typical cases, we want to mention rotation. But I mentioned rotation before I did rotation, okay? So if I do rotation first, then this follows from this, at least this part follows from this, even further away from here, okay? From where, from here. And there's a little more to status. I mean, you got Newton's third law is important. So not rigorous, but still pretty much tells you in summary what's going on. That's how it's applied. Okay, well. Totally analogous to what we do here with velocities and acceleration, we can do with angular velocities and angular accelerations. Now, one caution at this point, I could have said it back here, I was tempted to, I better say it now. Even recently, I've heard people say, well, average omega is theta over t. No. Okay, as I pointed out, I think t could be measured from any time at all. If you don't put a delta t in here, t is totally ambiguous. Okay, even if you know your delta theta is. Okay, you got the same delta theta, but you start your clock a minute earlier, you get a different result for your average angular velocity or average velocity if you're doing this. It's not theta over t, it's not x over t. Acceleration is not omega over t or v over t, it's delta on some interval between two events, okay? Delta means the change between two events. That's kind of inserted from clear blue out here, but it's time to assert it, okay? If I said it too early, you wonder what the point is, okay? Probably should have said it earlier anyway. But anyhow, there we have it. So alpha equals constant implies omega. Well, by the same exact analogous steps here. Okay. Wherever it is, here. No, come on, I wrote it somewhere. Yeah, here. Okay. Theta equals 1/2 alpha t squared plus omega naught t plus theta naught. And alpha equals negative k theta. Got myself in a box here. I'm not going to write that down. So it's going to be a little different order than what I wrote up here. I'm going to get the same stuff. So up here. Torque of a force, use the R vector cross. Okay. You might want to review that. I probably ought to draw a picture to go along with that. So you're just going to call this the axis. It's axis rotation. We assume it's a point or an axis. Okay, a line rotating somehow about x. You have a force here. And an R vector here. That's it. If you want to reduce this to scalar R, then you could use the R perpendicular to the line of that action of the force. So there's your scalar R. So you could just multiply by R times L, keeping your right hand rule. Out of that, should have gone through this picture, but there's your axis. So there's a picture that should remind you of everything I told you. And what we've seen with these rotating systems and everything in lab. Okay. Then I'll just stay with tau delta theta. Equals your change in kinetic energy. And I'm not going to refer to the derivation of that. Just for sake of time. Used up 2/3 of our time so far. Okay. I've used it up. You haven't done much of anything to sit there and absorb this out of wisdom. Okay. Okay, well, I hope you make it for another half hour. I hope you can hold your attention because it's pretty heavy. Okay, but anyhow, you got your tau delta theta, is your change in kinetic energy. From that premise, you get kinetic energy is 1/2 I omega squared. And if you want to work that out in detail, and we got a little more time, I'm glad to do it. Take more time than we got right now. Kinetic energy is I omega squared. Where I is the sum of all your masses times r squared. Every mass times its distance from the axis of rotation. And we've again been over all that in a good bit of detail. Or the integral of mr squared dr. Okay. So Newton's second law is I'll just state it for constant term. Now that equals I alpha. Instead of acceleration A, we have angular acceleration alpha, which would be in default units of radians per second squared, or at least angle per square time units. Okay. Net torque is force times the distance. Okay. So it's in units of meters times newtons if you're an SI. Okay. Meter newtons. I don't like to use Newton meters because it looks like joules. I distinguish between Newton meters and meter newtons just so we can keep track of what things mean. Your textbook doesn't make that distinction. That's fine. They know more than I do. I'm going to stick with what I do because it used to be fairly common. I don't know why people want to confuse things with joules now, but there's got to be a reason that I'm just too dumb to understand. Okay. And it might be simple as well. It just overrides confusion. I don't know. I think it creates more. But again, people have studied this. They've done research. I kind of trust them. I'm going to say meter newtons, or like I like to say, Newton meters, to distinguish the units of torque from the units of energy, because that can be confusing. You want to distinguish that. Okay. Okay, anyhow, we've got Newton's second law. The torque is I alpha. From this, we can say so I've already kind of set it up here. Okay. So this is just a little more general statement from this. This is a vector. Okay. And your delta theta by the right hand rule, you get 1 theta and another theta. Well, work that out. Okay. What haven't I done? We've got this. We've got this. You ought to look back at my notes to see if I'm getting anything. Oh, yeah. Well, naturally, we have the analogs to your definition of kinetic energy, your definition of momentum. So the integral, well, first of all, we'll just do tau net delta t equals the change in quantity I omega. Okay, so this is angular impulse. And this is change in angular momentum. And of course, I shouldn't have drawn a line there. And also the integral of tau net dt equals the change in I omega. Okay, this is also angular impulse. And this is still angular momentum. If you don't have a constant tau net, then you have to do an integral. Straightforward enough. Okay. So that's a whole lot. But then I hope to get all of your most basic mechanics on one board, but I wasn't able to do it. I've got another board, front and back. I have time to put everything down here. Still recording, but now we're out of focus. What the camera has about this picture of the aardvark. It really likes to see. Oh, camera doesn't even want to recognize the aardvark. Come on, there's an aardvark. Look, see? Okay, now let's take it back. Come on. Oh, maybe it's me and the aardvark. It just went into focus when I came into the frame. You'll work out the optics of this. If you do, we can skip optics. Okay. So let's hope we're staying focused. Okay, so let's see. Relations in isolated systems. Two objects. We have F12 and F21 being equal and opposite. This is Newton's third law of pair. By Newton's third law. I just wanted to write out Newton's third. I have way too much respect for the law not to write the word law. Newton's third law essentially gives us both. This is where the torques are calculated about a common axis. So F12 delta T was negative F21 delta T. Again, force on object 1 exerted by object 2, force on object 2 exerted by object 1. Yes, okay, so we're then for your talks, equal and opposite. There's details I'm leaving off, but that's the idea. That's the overview. That's the concept you need to really understand in order to see it as it manifests itself in a given system or a given problem. Okay. So momentum P and angular momentum L and let me write this. So your total momentum, which is the sum of your forces times delta T, has to be 0. Angular momentum, sum of your I omegas has to be 0 because you have two forces. You got F12 and F21, equal and opposite. You give equal and opposite changes in momentum, equal and opposite torques. They act for the same time. You know, while these things are acting on each other, they are doing exactly the equal and opposite thing at every instant. So we have this. That leads us to the statement of conservation momentum and angular momentum. Isolated systems. And what do we mean by isolated systems? That means interacting objects where all the forces are those exerted by the forces of one object on another. Okay? Take up all the forces exerted by any object on all the others, add them all up, you're going to get 0. Understand that in terms of 2 objects, then it's fairly straightforward to understand it for 3 objects. And as soon as you understand it for 3 objects, you understand it applies to as many objects as you wish. And there's your basis of thermodynamics. We'll worry about that second semester, okay? And not your whole basis. A lot of it. Okay. So I probably should have done that a little earlier, but I really wanted to do it generally in terms of both linear momentum and angular momentum. Show you that these are really not exactly 2 sides of the same coin, but closely related. It's a little easier to understand the structure of physics if you understand that. Okay, well, now we have gravitation. gonna write it out this way. Just using an R cubed in the denominator. It's a little less confusing if you see it with the inverse square explicit, and then the other R you understand as being divided into the R vector, the vector between the 2 point matches. And there's a picture of your R vector and the force. Oh. Need to start selling better chalk. That's the wrong color. All this. Now there are that smudge word is O-N, on. That's the force on mass little m. Now, if you want the force on mass big M, then your R vector goes from little m to big M. Goes from the mass that's exerting the force to the mass on which the force is exerted. And there are subscripts and stuff that we can do there, but okay, there's the picture. Okay, a couple of things. F is the gradient of your potential energy function. Where your potential energy is negative G, big M, little m over R. Potential energy is 0 at R equals infinity, at infinite separation, which means that if R is really, really big, big enough, then your potential energy is negligible, okay? Then potential energy is less than 0, so you have a graph of your potential energy function. Looks like this. Not very well drawn. It curves should have been a little smoother. Okay. Putting that on the chalk. I think it really was chalk that did it. Maybe not. Okay, so we have this. F is a gradient function, so it's conservative. You know that from multivariable calculus. Now, again, the multivariable calculus certainly isn't required for this course. So, you know, at this point, If you don't know multivariable calculus, then take my word for it. And my class here, give me a thumbs up if you understand that. Yeah, kind of a shaky thumb. No, it was okay. It was good. Okay. So my class confirms it. So it's got to be right. We can trust these people. Okay. And take a multivariable calculus course, you understand what we're saying. Okay, well. So the work done from point A to point B. Is potential energy at B minus potential energy at A. And that equals taking a big G, big M, little m over R2 minus taking big G, big M, little m over R1. Because your potential energy function is a function only of the separation between your two masses. So you go from separation R2 to separation R1. There's your change. That's our separation R1 at point A to separation R2 at point B. There's your change in potential energy. Now you work out the signs, that's going to end up with a plus. You can factor out your R1 and R2, and you get negative big G, big M, little m, times 1 over R1 minus 1 over R2. Don't worry about the sign of that. This is a quick review. I'm not going to get into that. Worth mentioning. Okay. Right there it is. You just got to work out what it means of doing some problems. Don't work it out unless you do the problem or have an IQ of 160. Okay. If you go to a good school, you'll probably encounter people with IQ in the middle of that range, maybe beyond. And you just kind of sit back and say, "Oh, that's really cool. Now let me figure this out myself." Okay, I don't understand how your mind works. Okay, well, so be it. As long as your IQ is at least 159, you're going to be okay. Right. 160 is like, I figure Einstein, Hawking, but a lot of people have IQs as high as Einstein and Hawking. Just those guys knew what to do. Okay, not a lot, but probably a million of them. I don't know. And work that one out. Standard deviation is about 4 standard deviations above, and you get to do e to the negative x squared, which you can make it. I kind of lose it after 3 standard deviations. I don't know. Way off in the tail of your normal distribution. That aside. Okay. So let me stop digressing and move on with what we're doing. A circular orbit. Gravitational acceleration equals centripetal acceleration. So your velocity is this. That's all you need to do. And then you work out your kinetic energy. You guys did this before. But let's review. So remember, 1/2 mv squared. Well, there's your v. You square it. You get big G, big M, little m. Put the 1/2 out here. And you get your kinetic energy, total energy. Well, here you got your expression for the potential energy, right? Inconveniently, it's right here, so I can draw an arrow. There's your potential. Here's your kinetic, and when you add them up, you get this. So now if you figure out, about to launch the Webb telescope. I just read an article kind of summarizing what we know about cosmology. Excellent article. Email me and I'll send you a link. I might send it even if you don't email me. I've kind of got it flagged. I just disappeared from the picture and I wasn't caught. Did I disappear there for a minute? You weren't watching, were you? Doggone it. Okay, well, that's all right. You were writing important stuff. You were off in your own world. That's okay this time for watching. Okay, if I disappear, we're not going to get to the end of this. With 5 minutes left, I don't know we're going to get to the end of it anyway. Okay, so anyhow, there's your kinetic energy, right? All right, there's your kinetic energy, total energy, potential energy. Okay, take the mass of that thing and figure out what its potential energy is at the surface of the Earth. It's not zero because you have to use this potential energy because gravitational force is not constant. Now, it doesn't actually change that much between here and orbital distance. But then we send it off about 1 million miles away where the sun's energy and the moon's energy. And so we're going to have potential energy due to the sun, potential energy due to the moon, different hours. Okay, and you integrate that and you figure out how much energy it's going to take to get to the Lagrange point. At this point, we've got a pretty stable orbit. The thing can do incredible stuff if it works. $10 billion project, 20 years behind schedule. And 9.5 billion over estimate. Worth it. Well worth it. It's less than the price of an aircraft carrier. Okay. And get back to close to the origins of the universe and able to really analyze exoplanets and stuff like that. It's pretty amazing. Okay, well, that aside, you figure out it's changing potential energy and it's changing kinetic energy. It's got to get up to orbital velocity, which you can calculate. Okay, say 300 miles above the surface of the Earth. So you know what R is, radius of the Earth less than 300 miles. Okay. And you know what your two R's are for your potential energy. So you figure out how much energy it's going to take to get that thing up there. Of course, the rocket also has to lift itself in its diminishing amount of fuel. So it's a really pretty cool thing. A couple of years ago, they launched the Parker probe, which keeps getting closer and closer to the sun. You can't just shoot a rocket at the sun because we're moving and that rocket's just going to go that way. We got to shoot it backwards at a speed close to the orbital speed of the Earth around the sun, which takes just about everything we got. We've never actually been able to hit the sun. Now we could, but it wouldn't be very good. Or it would take a huge rocket, cost way too much, and probably blow up. It's all very interesting. And a lot of the mathematics is right here. Now, when you get into the effect of the moon, the effect of the sun, the effect of Jupiter, got to take all that into consideration. It's a little more complicated. Potential energy function is still what it is, except those things are moving. Well, get into square mathematics. Okay, well, the Hubble and the Parker probe were the two coolest things that have happened in the last decade. And, okay, we got 2 minutes, and all we got to do is simple harmonic motion, right? So there's more. Actually, I do need to do a little more here. So maybe I'll save simple harmonic motion since that's the current topic. We'll take care of that pretty quickly. Typical orbit, take a circular orbit, and then give it a push in that direction, it becomes an elliptical orbit. Okay. So you got the planet here, and you got an orbit. The planets are the focus of the ellipse, which is not hard to prove. We haven't gotten into that mathematics, and as y'all probably don't have the expected command of conic sections, probably mostly due to COVID interfering with your education. We're not going to get into that, but you want to understand it. An elliptical orbit with the planet as the focus, and you got your, this is your mass big M, this is your mass little m. For R vector, you want to get the force on mass little m, looks like this. Okay. So the force on your little mass is here. The torque is 0 because your R cross L. Now again, you got to understand that the cross product has a magnitude equal to the product of the force in the R vector multiplied by the sine of theta, theta being the angle between the R vector and the force, which is 180 degrees, and the sine of 180 degrees is 0. Okay. This thing's not exerting any torque because the line of action goes right through the big mass. Okay. So sum of torque is 0. The angular momentum doesn't change. Okay. I'll be faster when it gets closer. That's one of Kepler's laws. It says that the radial vector sweeps out equal areas at equal time intervals, not just equal delta t. Or it sweeps out area at a constant rate. Let me say a constant rate at which area is swept out with respect to time. Okay, we're a few minutes over time. There might be some stuff I left out because I stopped referring to my notes here. Let's get started. We'll just go. Okay. And we still have a lot of motion. Okay. And we already know how to get the equations of motion. So we got a velocity function. We got a kinetic energy function. So I'll just say this much. We can say that if you multiply that by omega. Okay. Remember, B is d theta dt, right? And theta is a cosine of omega t. I hope I wrote it that way. Let's make sure I didn't mess up. Yeah, we use. I said d theta dt. dv dt because we're not torsion. Okay, so anyhow, energy is this. There's your kinetic energy, there's your potential energy. And I think we've seen this for a long time. Okay. Matter of fact, at least one of you keeps wanting to use this. Okay. Sometimes appropriately, sometimes not. I think you got that sorted out now. Okay, so your kinetic plus potential energy is this. If X is a cosine of omega t, I said omega a cosine. And it's a negative here. But I'm not going to worry too much about that. That's 1/2 L times okay, just for X equal a cosine omega t, V has to be the derivative of that, which is negative omega a sine omega t, right? So we get this. Okay, we're getting well too far over time. I'll let you guys go. So here I'm gonna have to do something like this. You might want to simplify this expression, knowing that omega is the square root of k over m. Okay. Okay. Well, that's a simple, easy simplification, but yeah, you've just got to be about out of it by now. And now I've noticed that the stupid camera went out of focus again. So I don't know how much of that anybody was able to see on the video, but both the artwork, maybe we have it, and it's still out of focus. Doggone, it just makes me mad. Okay. But I don't have the energy to throw it. Okay, give me just a second. I really have to try to get this in focus. How stupid can you get? Oh, it's in focus now. All you gotta do is insult the thing and it goes in focus. Remind me of that next time. Okay, or just sit back there throwing metal insults. That might be too. Or you turn the camera off and then you can make noise and everything else. So I don't know how long it was out of focus.